Welcome to another Teacher Tobin video. We're going to be talking about Bitmap Images, which is part of topic 2, and it will cover the 2.2.2/4 specification for the mapping, and it's to do with Edexcel GCSE Computer Science. It will help you revise this topic. The key to understanding any questions about Bitmap Images is not to be lost in jargon, because you'll hear words like size, right? And what does that mean? That could mean, let me change the color, it could mean image size, or it could mean file size. And then there'll be another word there, resolution. Okay, so, and more vocabulary, color depth. So there's lots of words that you've got to be really careful of. And then we're also going to be, when you have questions on this in the exam, you're typically going to be dealing with conversion issues for megabytes. Okay, so we've got to know what that is. So we'll have a look at all those different things here. So let me just start off with a very simple bitmap image. Let's say of a little arrow that you might find on Word or PowerPoint. The number of colors here, we just got black and white, this grid of 16. So we could say, if we just need two colors, black and white, that is 2 to the power of 1, all right, and it's 1 bit per pixel. 1 bit per pixel. If we wanted 4 colors though, we wanted to improve that, we wanted to have more colors, we'd have to have 2 to the power of 2, and we'd need 2 bits per pixel. So forth with 8, 2 times 2 times 2, and 16. Okay, so we've got 3 bits, 4 bits. There we go. So another word that you might come across is bit depth. So we'll add that to our jargon list. Bit depth. Okay, so let's just take a little step back for a minute and look at all these different things. So we've got a picture here, and on the screen, on your computer screen, your screen is made up of pixels. For something printed, it's dots. So you might see things like DPI being mentioned, and typically for print quality, it needs to be 300 DPI for anything that you're going to read, like a newspaper, a magazine. Dots per inch. For pixels per inch, if you want to have the equivalent, I probably want around, like retina displays were about 330-ish. So pixels per inch density, so you can not discern the sort of little edges around characters and things like that. So very simply, image size could be the width. Okay, the width. Let's say this is 1024, and the height, and let's just say that that's 800. I don't know for sure exactly what it is, but it's about that. So 1024 times 800 would be the image size. Okay, so that's the image size. That's an easy one there. But that's not the same as file size. Okay, so we've looked at image size, but be careful, because it is going to be different when we talk about image size. And when you see pictures that are sort of fuzzy and they don't have a lot of detail on them, that's when we talk about this concept of resolution. Now, I got this royalty-free image from Dreams Time, and it was just a preview, so it's not as good resolution as the original if I downloaded it. which would be at least 300 dpi, ready for printing. Lossy compression images like JPEG, where you've lost information, typically mean that you've lost resolution there as well. The information is sort of gone. And let's look at color depth for a minute then. Okay, color depth. So let's just go back to this idea. If we wanted to have, like in Photoshop, you might now have 24-bit images. That is going to be the number of bits we need. So I'm just going to put a line under there just to make it a little easier. So we don't have that many colors here. We've only got 16 colors, so we need more usually. Right? Let's say we've got a GIF, an animated GIF. That's usually 256 colors. So how could we represent 256 colors? Well, 2 to the power of 5, 32, 2 to the power of 6, 64, 128, 2 to the power of 7. And when we get to 2 to the power of 8, I'll write that again, 2 to the power of 8, we get our 256. And that is going to give us 5, 6, 7, 8 bits. So an 8-bit image can have 256 colors in it. All right. But if you've got a really good image from your camera, it's now going to be usually 24 bits, which is about 16 million. And what would that be? It would be 2 to the 24. That's 24 bits. And the amount of colors is about 16 million. In fact, I can probably work it out quickly on the online calculator. Not that you would need to do this, but just to show you. So in Photoshop, if you're dealing with 16 million colors, you'd need 24 bits to store that information for each pixel. So this is each one of those tiny little dots on the image. Each one of those tiny little dots, one of those pixels, would need to be 24 bits in length to have 16 million colors associated with it. The potential of 16 million colors. It might just be one color, but you could choose from over 16 million colors for that particular pixel. So let's go now to have a look at what image file size is. File size. And the file size is the width, what did we say, 1024, the height, which we said was 800, and then the bit depth. Okay, and we need to times them all together. So width times height times the bit depth. So let's say this image of the dog reading newspaper is 24 bits. The file size would be 1024 times 800 times 24. Okay, it would be 1024 times 800 times 24. That would give you the better. That would give you the file size of it. And we'll go through some example questions in just a moment from exam style questions. So hopefully so far you've got an idea of at least what the image size is, and that it's different from the file size, which takes into account the bit depth. And then to have bit depth, we need to know how many colors to represent for each pixel. And if you had just 1 bit per pixel, you can represent 2 colors because you've got 0 and a 1. Binary, it's 0 and a 1. You can store that in 1 bit. But if you've got the 24 bits, then we can represent up to over 16 million colors for each pixel. So this part of the dog here is going to have a lot more colors than just say this black and white area. So let's look at some real questions. Let's look at some real questions. Let's start with an easy one. Computers store and manipulate data. State the number of colors that can be represented with 5 bits. Okay, so if you've got 5 bits, 3, what am I doing? 3, 1, 2, 4, 8, 16. In 5 bits, if we had 1, 1, 1, 1, 1, what would be the biggest number? Well, it would be 1 less than the next column here, so it'd be 31. But we also have the black, which is 0, 0, 0, 0. If we had 0, 0, 0, 0, we've got between 0 and 31. So in total, it would be 2 to the power of 5 equals 32. So let's go back here. 2 to the power of 5, which is our 32. That gives us the answer there. We can only have 32 colors if we've got a bit depth of 5. Let's have a look at another question that's not too difficult. An image has 1024 times 1024 pixels. So it's a square, 1024, 1024, and a color depth of 24 bits. State the size in megabytes. So it's not the same as megabytes here, it's megabytes. It's not that difficult actually. Here you would just say 1024 times 1024 times by 24, the bit depth, and you divide by 8 because we're not dealing with just bits. We've got 8 bits equals 1 byte. So divided by 8 gives us the bytes. And mebi is related to, if you can remember, a megabyte is a million. A mebibyte is a base 2 system, not metric. So we've got the 1024 to the power of 2. Gives you these two here, 1024 to the power of 2. So it's very typical that they'll ask you to, they'll never, in the exam, they'll never expect you to do the calculation outright. Let's have a look at another one. An image with 24 bits has dimensions 440 times 330. So 24 bit is the bit depth, 440, 330 pixels. Construct an expression to calculate the size of the file in megabytes, right? So we would do the width times the height times the bit depth. Okay, so that's definitely going to give you a mark. If this was a 2-mark question, you're going to get a mark for doing that. But now we need to make sure that we're converting to megabytes. Okay. The kebibyte is 1024. 1024 to the power of 2 is our megabyte. And if we kept on going to the power of 3, we can go higher. All right. So we would need to make this work, have 1024 times 1024, and then also the 8, so that we're dealing with bytes and not bits. So you could have it in any order, but this is an expression. You would never be asked to calculate that in the exam. You would just be asked to write an expression. So let's look at another one, an exam from a real exam. A pixel is the smallest element in the bitmap images. Two images are displayed on the same screen. One image is, okay, so, and the second image has a higher resolution. Okay, so state one reason why the second image will be displayed in more detail. So if it's high resolution, I mean, this is, don't overthink this. If it's high resolution, it's going to have, you could say that this is going to be, sorry, I'm just getting my bearings here. PPI, pixel density, the amount of pixels per inch, is higher. PPI, I think they would accept PPI, but if in doubt, just say pixels per inch, and or density. Okay, either of those would give you the 1 mark. Okay, so how many pixels are there? So I'll just go back to this. If this was a web image, it might be 72 PPI for like web. If it was for something that was going to be more mission critical for like a textbook or online magazine, then it might be going to this sort of retina display style density where you have more pixels per inch. So for every inch, you've got a lot more pixels to use. Sometimes this could also be 96. It used to be on a Mac. But you could just need to know that how many, if you can pack more pixels into a small space, you're going to have a higher resolution. Okay, let's look at the second part of this question. A 10 color bitmap image uses 15-bit color depth. The image is 1082 by 640. Complete the expression. Okay, so the top bit's relatively straightforward. We've got width times the height times the bit depth. Okay, so width times height times the depth. We need to have that. Now we need to do the conversion. Again, it's this megabytes. And kebyte is 1024. Timesing it by 2, which is also the same as doing this, will give us our megabyte. And then again, because it's a byte, we want to not look at just bits, but bytes is 8 bits. So that would be enough to get you your 4 marks. You would need to have this in the numerator. You would have to have this in the numerator, so that would be a mark. You would need to have this in the denominator, and you'd need to have this in the denominator. They've helped you out a lot by adding the 1024 in here, so that if you forgot what a megabyte was or a kebyte was, then it would really have helped you understand the conversion. And just to go over that again, I did it in another video, but if we've got our binary 64, 128, 256, 512, 1024. Okay, so that's 2 to the power of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 2 to the power of 10 gives us our 1024. All right. Hopefully that helped. If I know it's a lot of information there, but if it did help you, let me know. If you want me to do more on this, let me know, and good luck.